So welcome to another tutorial of the electronic circuit and design. Today we are going to simulate the differential amplifier using the LM741 operational amplifier IC using the LT Spice simulation. Okay, so what is actually the differential amplifier is? The differential amplifier is basically the amplifier that actually amplifies the difference between the two inputs. One is the VN1 and VN2, and it amplifies the difference at the output. So the output of this type of the differential amplifier is given by the gain of the differential amplifier and multiplied with the inputs, which is actually the difference by its definition. So it will be V in 1 minus V in 2, and sometimes practically they write it as the V of the positive terminal subtracted by the negative input terminal. So here the AOL is the differentiator mode voltage gain. Okay, so there are basically the different categories of the differential amplifying working stages. Let's see them step by step. Alright, now you might have observed that in case of the differential amplifier, sometimes the term is being used the common mode rejection ratio, and for any of these amplifiers such as this LM741, from its data sheet you can easily realize this factor is being given. The common mode rejection ratio for this RS should be less than 10 ohm, and VCM, which is a common mode voltage, should be applied between the plus minus 12 volt, and it has the typical the gain of this common mode rejection is for this type of amplifier is minimum 80 dB, and typically it's on 95 dB. So we will be looking this factor in this differential mode of the amplifier, that how we are going to evaluate this parameter, how we can use this parameter, and what is the importance of defining this ratio. Okay, so moving toward that, first of all, let's just consider that there are two cases for using the differential amplifier. In one case, such as this diagram, here the V in 1 and V in 2 are two different voltage level, and that means that they might have different frequency if it is an AC signal, and in this case the output voltage is actually equal to the open loop gain, which is the differentiated mode voltage gain, and multiplied with the difference in the input voltages. Okay, this is the differential gain. Now what if the both of these inputs are same? That means if I common them up and supply the same voltage source on the both of the terminals, so in this case the output of this this differential amplifier must be equal to 0. This is an ideally the ideal output of the differential common mode amplifier is 0. So because the difference between both of these inputs are same, so that means the V in 1 and V in 2, if they are same, then it is also called as the common mode amplifier, and plus the since the difference becomes 0, so the output should also become 0. However, in practical cases there is some output voltage appearing over here that is very much small, but it usually appears. So practically, whenever we are using the output equation for this common mode amplifier, it's actually equal to the differential gain multiplied by the difference of the voltage plus the common mode gain and multiplied with the common mode voltage, whatever it is appearing over here. So this factor VCM, which is the common mode voltage, should be very much small as much as it is possible, because ideally it must have the 0 output, but usually it gives some amount of the voltage that is in millivolts, even less than that. Okay. Alright, now let's just discuss the application of this differential mode amplifier. Suppose that I apply the V into signal that is supposed to be a very low frequency noise, and I have combined it with the another resistor that is being grounded, and I'm supplying some sort of the voice over my V in one terminal, and I need the output that is differential. So what is the function over this differential amplifier over here is that it must be capable to suppress this noise and must prevent it from coming toward the output. So ideally, if I look at by the definition of this differential amplifier, ideally the differential amplifier must be capable to suppress the common mode input that can be noise or any signal, whatever you are providing it over here. Okay, so let's just now just summarize the common mode gain of this amplifier is that ACM, that is the common mode gain, it is equal to the V output, which is common mode, multiplied by the common mode voltage over here, that is over here. Okay, so let's just move ahead and let's see how we can define the common mode rejection ratio. Alright, now by definition, the common mode rejection ratio is the ratio of differential gain to the common mode gain. Okay, now you might have observed this differential gain from this picture, and this is the open loop differentiator voltage gain. So what is actually the common mode gain? The common mode gain, if you look at into this picture, it's actually equal to the output, that is the common mode output, divided by this common mode voltage. So keep in mind that this ratio, this common mode ratio, should be less than 1, otherwise this factor VCM, which is the common mode voltage, might increase. And earlier I have told you that this factor should be in millivolts and much preferable less than that, even less than that. Okay, so you can also express this CMM, the common mode rejection ratio, in terms of dB, where it's equal to 20 log of the common mode rejection ratio. That you can also mention it as the differentiator gain divided by the common mode gain. So it will give you the answer in the decibel, and in normal cases usually the data sheets also use the decibel units. Okay, now let's just move toward the example so that we can easily understand how we actually use this differentiator in suppressing the noise, and I hope so that it will be clear. After that, we will be using the LT spice to observe our outputs that we have usually calculated from the simulator, and as well as the theoretical analysis using numerical problem. Hello. Now let us just take an example in which we want to know that if we have a amplifier in the differential mode, and given that it's a LM741, and based upon this data sheet, we know that typically our CMRR ratio, that is the common mode rejection ratio, can vary between the 80 to 95 dB. Assume that it is 90 dB, and we will check that if we connect the common mode voltage, and let's suppose that it's a noise signal whose amplitude is 2 millivolt with the 50 Hertz frequency. We will check that how much this common mode input voltage is suppressed at the output side. Okay, for that purpose we assume that we have two resistors. One is R1, that is 1 kilo ohm, R2, that is 10 kilo ohm, we need to check how much noise can be suppressed by this amplifier if the differential input voltage, which is the difference between these two nodes, is actually 5 millivolt, and a 1 kilohertz is the specification of this differential voltage that is being present over at these 2 points. That means that for the sake of the second, we have removed this common mode voltage, and we are applying some 2 different sources, one V1 and V2, whose difference is the 5 millivolt and the 1 kilohertz. Okay, so what will be the differential gain A of D? So from this circuit, that's very simple, that A of D is actually the ratio of R2 over R1, that is the ratio of the output to the input resistance, that makes it 10, and the expected the differential output voltage for this given gain and the given differential voltage, that was V1 minus V2. We can place the values R2 over R1 into the differential voltage. So 10 into 5 millivolt, that will give us the 50 millivolt at the output, in case when it is having a different inputs V1 and V2. For the specification being given over here is the 5 millivolt difference input signal. Okay, now if we replace this differential input system, that means if we replace the V1 and V2 based upon this type number 2, in which we will apply the same signal at the positive and the negative terminal, that means the inverting and non-inverting inputs of this amplifier. For the specification given over here is that V of n, which is a noise signal, whose amplitude is 2 millivolt with a 50 hertz frequency. If we apply the same input at the 2 terminals, this makes it to behave as a common mode and differential amplifier, common mode amplifier. Now let us just check the impact of common mode input voltage, that is being by connecting the V of n. Given that we have a common mode rejection ratio for this type of the amplifier is 90 dB, and we also know that the CMRR is actually equal to the 20 log of the ratio of the common mode rejection ratio that was specified above, AD over ACM, that is the ratio of differential gain to the common mode gain. Now if I drop the values 90 and 20 and just try to find out the value of this common mode gain, because I have already found this differential gain that was 10, and we need to find the common mode gain. So by simplifying the circuit, that we obtain as the common mode gain is actually equal to 10 divided by 31623, that makes it 31,623. So if the inputs are being common, so what will be the output voltage in the common mode situation? That's very simple. The output of this terminal will be known as the common mode output, that will be equal to the gain of this amplifier and with the input signal, the common mode signal. In our case it is 2 millivolt, and the common mode gain is 10 divided by 31,623. If I drag the values and substitute them, then it can be seen that the output voltage in the common mode situation is 0.63 microvolt. So I told you in the previous case that ideally when you actually apply the same input, that means the common input at both the terminals, the output should be 0. But practically it is not like that, because you are considering the gain of the system as well as all those constraints. So you get actually a very minute amount at the output, and typically it should be less than a millivolt. So in our case, through the calculation, we have seen that the output common mode voltage is 0.63 microvolt. Now from all this calculation, what it actually tells us? It actually clarifies that how well our common mode input is being suppressed. we actually supplied the 2 millivolt signal of the noise with 50 hertz frequency, and at the output during this common mode condition we are receiving only 0.63 microvolts. So you can easily realize that how the differential amplifier is working. Also, since this differential amplifier is also depends upon the on the frequency, so let me illustrate you what will be the impact of the frequency over the dB. So let's check, let's see the relationship between this the common mode rejection ratio and the gain over the frequency. Now you can easily observe that as the frequency is increasing, the ability of our amplifier to suppress the noise is gradually decreasing, because this gain is inversely proportional to that of the frequency. So as the frequency increases, the ability for our differential amplifier to suppress the input noise will gradually decrease. So I hope so that you have clearly understood this concept of CMRR, and through this example. Now just let's move toward the LT Spice, where we can analyze the bandwidth and the impact of this frequency over the gain, as well as this how this whole scheme actually works.